Alright, in this one here, where we're trying to find the shear and bending moment diagrams, we've got a beam that has two concentrated loads, probably coming from two beams that frame in out of plane. They're located at the third points of the beam, so that's L over 3, L over 3, L over 3. That symmetry tells me right away total load gets split evenly between the two. So there's our reactions. And so now I just apply everything we learned about basic relationships between load, shear, and moment. We have no distributed load, so that tells me that the shear diagram is going to be contained of regions that have zero slope on it. And sure enough, and let's just rewrite them once more. dV dx equals W. And in this case, W equals 0 throughout, so I know the slope of the shear diagram is going to be 0. So I just follow the loads. We go up by P. 0 slope over to the next load that happens. So, hey, that goes down by P. So we end up with 0 in this segment. And then it's flat. So we get to the next concentrated force. And so then that goes down by P, comes over, and goes up by P again. And we have shears that have three different values in those three different segments. The moment starts at 0, and the slope of the moment diagram is given to us by the shear. The shear is positive, and it's a value of P. This length is L over 3, as are these other three segments. So that means we'll have P times L over 3 would be the value there. Then the moment doesn't change because the shear is 0. So that's nice and flat to that PL over 3. And then we have a minus PL over 3 for this area. That takes us right back down to 0 with a slope of minus P. And there's your moment diagram. Kabam. Now, that's pretty quick and easy. I want you to not forget something really important here. Let's go cut a free body diagram just to the left of that first concentrated load. Right, and I'm going to put that right down here. And it's just to the left. Okay, so being just to the left, note what's going to happen here. We have the reaction of P, we have the shear showing up here, and we have the bending moment that shows up here. And we've got this distance x, right, now that's anywhere in that region, right, so the moment increases with x, P times x, and that's exactly what's happening here. The shear is constant, P equals P, and then right where we're just to the left of point P, at the L over 3 location, then the moment equals P times L over 3. That's exactly what we said. And there's your equilibrium that proves that that's the case. Now let's take and go just to the right of that load. Right, so now the load shows up. We're just to the right, so there's your V, but P equals P, so V has to be equal to 0. That's exactly what we've got showing right in that little segment. And then the bending moment, well, as it hops right onto the other side, it really hasn't changed anything here. It's still L over 3, right? PL over 3, because this applied load doesn't have a moment arm just immediately to the right of that, right? Now, as we walk our way then into this section, you say, well, now this one picks up a moment arm, but that's going to be equal and opposite to the moment arm that's added to what you have to the reaction effect. So that's why you end up with 0 moment going throughout that whole middle segment. Never forget these free body diagrams that are going along with each location in the shear moment diagram. And indeed, you should be able at any one point be able to come in and draw the free body diagrams that are associated with those specific values or combinations of shear and moment. Hint, 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 that'd be a great quiz and it'd be a great test question.